So today's topic, we're going to talk about rubber elasticity series. We're going to continue to talk about that. So in the first sort of half introduction we did the other day after exam, we talked a little bit about what is stress, what strain is, and we stopped at this stress strain plot. So this is the most commonly mechanical problem. So we're going to continue on this part, and today we're going to talk a little bit of difference between the rubber elasticity for rubber versus a metal piece, and explain to you guys what's the similarity and differences between two kind of different commonly used pieces for springs. So for this part, last time we talked about how do we get the stress. So this would be equal to the force divided by the area. And strain is given by the deformation of the polymer, or deformation of any kind of material, divided by its original length. So if you stretch something 1 centimeter to 2 centimeter, your strain will be 100% or 1 in that scenario. So another part that is relevant to deformation is Poisson's ratio. So this is a concept in mechanics describe what is the deformation of the polymer in the deformation direction that perpendicular to where we are stretching. So here is a good example. So you can see we draw two rectangular shape. So the black rectangular shape represents what is the sample before we pull it. And the gray part is the deformation after it's being deformed. So if something is elastic or elastomer, we usually deform in one direction but shrink in the direction that perpendicular to it. So if you have a rubber band, you pull it, you will see it's getting narrower and narrower. So this is the effect related to that. You can see in this direction, your rubber band gets narrower. So the Poisson ratio is a descriptor to tell you how much kind of deformation you had in the perpendicular direction. So how do we define this Poisson ratio V? So it's defined as what is deformation in the direction that is perpendicular to the stretch direction. So you can think about this would be delta W would be the W minus W, W0 minus W. So W0 would be original width. W would be the after deformation, how much become. So delta W would be how much deformation you had. So in this case, we can calculate this delta W divided by original W, or in many other cases, you can see it's also related to delta D. Different ways we can present that. So Poisson's ratio is basically how much shrinkage you have. So it will relate to the strain. So this is the strain what we talked about. So how much deformation in negative sign is related to this deformation direction. So let's use example of this. If we stretch the rubber twice the length, if it shrinks half of units, that means it's Poisson ratio of 0.5. Okay, that would be the scenario when you look at the case when you have stretching a perfect elastomer because of conservation of volume. But many other elastic, non-elastic deformations, such as plastic deformation, that means you only elongate in one direction. You don't have a lot of shrinkage in the perpendicular. It's possible happen that way. And we give you guys a range of different material. What is their Poisson ratio? Water has a perfect 0.5 because when we deform the water or when we change the volume is always conserved, right? We don't lose or add water molecule, so you shrink 50% when we double the length of the other direction. Okay? Amy, wait, we haven't finished yet. I'll call your name once we. So there's a few other that we talked about. Natural rubber, cross-linked, is very close to 0.5. Gels, etc. So most of elastomer that we're talking about is related to that. It sort of behave like a perfect elastomer. Then there's a lot of polymer is like plastic deformation is dominant. You can see it will be below 0.3. It's possible you have 0. 0 means it just elongates. It doesn't shrink at all. It's sort of a little bit strange phenomenon. Most of polymer don't have a 0 Poisson ratio. That means you grow taller, you didn't get narrower. That's absurd. So these are non-traditional. And most of inorganics, steels, you can see this has a relatively low Poisson ratio. So you can pull a steel, elongate them without much shrinkage. Poisson's ratio is also related to other physical parameter that we're going to talk about is elastic modulus and shear modulus. We will talk just in a second. In this case, G shear modulus is related to the 2 times 1 plus Poisson ratio will equal to E. So in terms of plastic, when your Poisson ratio is 0.5, your elastic modulus will be 3 times shear modulus. So these are somehow related. But most important is everybody need to know how do we define the Poisson ratio, which is how much shrinkage you had in the direction that is relatively perpendicular to the strain direction, okay? So Amy, you have a question? Yes, please.
I was just hoping you could redefine that equation with the variables in that diagram.
Oh, it will be, Poisson ratio will be, so delta W divided by W is equals to Poisson ratio B times, okay? This would be the strain. Strain will be, we didn't draw anything in there. So if we have to say something, that will be delta L divided by L0. How much changes in the length direction? Minus what is, divided by what is L0, which is original. I mean, pretty straightforward, right? Those are basic mechanics. All right, so this is another part is in stress and strain, we typically, sometimes people discuss 2 different terms, one called engineering stress, the other is called true stress. So let me explain what the difference. So we discussed at the beginning, your stress is given by the force divided by cross-section area. But in some of the polymer, when we have deformed, we saw in the Poisson ratio that your cross-section area will shrink while you stretch it for elastomer. So technically, your force is the same, but your area that your force is exerting on gets smaller and smaller. So that means your stress is changing over the process of stretching. So that's where these 2 different terms are given. So one is called engineering stress, which is just, we don't consider changes in the cross-section area. We only look at the force has been happened on the sample divided by its area. And then we use this constant area term to get the stress, okay? The true stress will be given how much the area that we are looking at. Because when we stretch, the area shrinks. So this would give you example. This would be, let's say we are stretching a polypropylene sample dog bone. So this would be original sample shape. And when we do put in the instrument, we measure the stress strain curve. This would be what's happening. It appears your force is dropping after a certain strain. And this force drop is correlated to the necking phenomenon. So, which means there is a narrow area is formed, then this narrow area will grow in length. So the black line is the engineering stress strain curve. The dashed line is true stress and true strain curve. True stress, we didn't plot true strain. It's just the true stress with the engineering strain. Okay, I misspoke there. So this would be what the stress, as you can see, it's continued increase. It didn't have a drop. The reason it dropped here, apparent, is because we now have the force exerting on a much smaller area. If you consider the drop of cross-section area, your force actually is continued to increase. Okay? So how do we get the true stress from the engineering stress? It can be done by looking at what is the what is area that is changed. Okay, here we need to make a assumption is how big the sample cross-section has changed. So we typically just apply a very commonly used called constant stretch area, constant volume assumption. Okay, so what does constant volume? That means before we stretch and after we stretch it, make it longer, but the total volume is the same. Okay, so from the change of the volume, we can from the constant volume we can get the change of the cross-section area. So we just need to know what is A0 with respect to this A1. Let's call it 0 and 1 just to be consistent. So the length, this is the length 0. This is after we stretch, we become length 1. So the volume is area times length. This will be the same. Does that make sense, everybody? So we just need to rearrange it a little bit. We can get to what the area difference is. So the area difference would be A1 divided by A0 will be L0 divided by L1. And if everybody knows, this is 1 over lambda. This is called draw ratio, or it's equals to 1 plus strain, which is the other way we can present it. So then we can calculate what is true stress. True stress would be force divided by area A1, right? That will be the new area we are looking at. That will be equals to force. A1 would be equals to, if we rearrange this, A1, from this equation we can get A1 is basically equals to A0 divided by draw ratio. So the bigger you pull, the A1 will be smaller and linear proportional to that. So if we apply what this equation is, we can get the true stress is basically equal to engineering stress times draw ratio, as given by this equation. Okay, pretty straightforward. So that means the higher the draw ratio, there is bigger discrepancy between the engineering stress and true stress. If the rubber is being drawn 5 times, although the force you measure then maybe only increased 2 times, but the true stress has to be twice times the draw ratio is 5 times. So this applies to here. Before that, we don't for any necking. Once we for necking, the cross-section area is much smaller. Okay. And there's also a description of the strain. This is called true strain, also called a Hecking strain. And it's used less. The definition is shown here, which is basically true strain. This is the T just means it's a true strain. It's integration from the initial length to the where we are draw and integrate with dl. So it's basically log in L divided by L0. Or this would be log in draw ratio. Okay? That will give you the true strain. Okay, so with these basic definition out of the way, we're going to talk a little bit about property of polymer. So when we think about physical property of the polymer, we need to think about the physical state of any material. Particularly in the condensed matter physics, what we mean physical state is how those molecules are arranged with each other. So polymer is a class of polymer that is notoriously known for their disorder. A very distinct difference compared to metals and ceramics is where polymer is in amorphous state. So what the force holding the polymer chain together, chemical bonds going to hold your atoms together. If you have polymer charge, charge force will be. And the weaker force would be van der Waals force or dipole interaction. These we talked about. The most preeminent one will be van der Waals force. This is very weak, short-range forces holding the polymer together. That's what makes polymer flexible and ductile compared to aluminum or other metals. There is an interaction, there is a constant fight between what the force holding the molecule together versus force that will make the polymer disintegrate. Okay, will make them randomize. That is thermal energy. So thermal energy is a type of energy that allows the polymers to become disordered and become randomized. So we need to understand a bit better for rubber elasticity theory. We need to understand how does these two forces are interacting with each other and how these could result in different state of matter. Okay, so in the following slides, we can look at, in one case, if you have low molecular weight structure, such as crystals, liquids, gases, if you think about the liquid, this would be a great example that when you heat the liquids, gases up, when you heat the liquids up, they will become gases. And this is because we are breaking the interaction between different atoms. So the atoms are held together by this van der Waals force or dipole-dipole interaction. Pretty similar like we talked about in the chi parameter, we talked about cohesive energy difference. So this would be one of the type of force that holding the polymer together. It's mostly is entropic driven. So when you change it, you're changing the entropy of the system. And this is directly related to evaporation phenomenon or changes of the, for example, atoms in a lattice. When you deform a metal, you're deforming the atoms in the lattice. This would be one way. When you heat, it will evaporate. When you cool down, it will come back to the original shape. So in this case, you are also changing the entropy, which means the entropy of the system is being changed. They're going from high temperature states, you have higher entropy in that state. Okay, coming down to here, we also need to talk a little bit about motion of the molecule because it matters for elastomer that we have to be in a mobile state. Mobile state, that means everything needs to be able to move that relate to the motion of the molecular as well as the glass transition phenomena. So have everybody heard about glass transition temperature? Okay, so this would be the example that we have to know. For all the rubbers, one of the condition is it has to be mobile at room temperature. That means all the elements in the rubber are going to have low temperature. So Tg of your rubber monomer need to be way below room temperature. Polybutadiene is an example. It has Tg about minus 70, 80 degrees. So rubber is mobile. So in this case, it's important that your atoms can move from one position or molecular from one place to the other. Free volume will be taught next semester by Sergei Nazarenko. He's really like talk about free volume. I'm sure you will learn a lot about that. This is related to the cooperative motion about different elements, atoms within a molecule, how they move. Okay? So at the high temperature, the thermal force will win the battle and free volume is very large. At low temperature, the thermal force or the temperature resulting in vibration will lose the battle and free volume decreases. And this matters a lot because when you don't have free volume, you become glassy. So which means your polymer cannot move. And the other part that we haven't talked about is crystallization is another way you can frozen the polymer and let them stay there and not move. So you effectively can use crystallization as a cross-link method. Okay, so in order to get a rubber, we definitely need low TG material, and it needs to be cross-linked. Depending on how you cross-link them, we discussed there's two ways we can generate a rubber. One way is we can generate a physical cross-link that is typically forming a glossy domain. So in this case, it will be low temperature. And in some reasons that you would have a polymer would also be able to form a glass just because you have a chemical cross-link. That will be using the sulfur to cross-link the rubber. Okay? Okay, so polymeric material is slightly different. Polymeric material is also governed by a lot of entropy in the polymer. That we will discuss later, that rubber in the polymer is actually a very important entropic elastic. So in the polymer, because we now have connected, we no longer has individual atoms, both polymer chain will be able to move within a segment. So very important is we need to have these segments as mobile. If you think about this polymer chain, everything is frozen, you don't have a rubber. You can't cross-link, let's say, a polystyrene to form rubber. It's still going to be a rigid material. So every segment in the polymer has to have the mobility. And that's why a lot of the time the rubber has lower temperature limits. You can't go too low because rubber will become glossy as well and become losing its ability. And this is related to the rubber need to be able to be mobile. Okay? So this is done by rotation and changing the segment. It's very much similar to like we talked about in the first part of the lecture, all these conformations changes when you stretch the rubber. Okay? So any questions so far? Not much? Okay. Okay, then let's keep going. So the rubber theory is discovered in the 1940s by several professors. They use a very simple theory to deduce what is a rubber and how rubber elasticity came from. And before that, rubber already become a very important product because a lot of things happened in the Second World War. A lot of area requires use of rubber. And rubber is definitely a highly sought wartime merchandise that people need to chase. So the theory comes out just in time for everybody to understand. So we're going to talk a little bit about the thermodynamics of the rubber. So that's related to this slide, where we're going to talk a little bit about thermodynamics again. Amy, please.
Sorry, my question is a little bit back. I've heard TG defined a lot as segmental motion, but like,
yes.
How long is the segment for it to be segmental motion?
Oh, good question. So TG depends on instrument. It will report different values. So there's no universal ways it has to be this segment or not. As a matter of fact, even for different instrument using different measurements, it will report different value. So there's no rule of thumb, let's say 1 segment or 2. But what you need to know is what within a few segments, let's say 3 to 5-ish, it starts becoming mobile. It's no longer fully freeze. But this parameter depends on how fast you cool. If you use DSC, how much you cool it. So the cooling rate that everybody uses or accustomed is like 10 degrees Celsius per minute is the range when you measure the TG. If you use Rheometer, it's really, or DMA, it's usually measured what's the tensor delta peak at 1 Hertz stretching rate, okay? If you change the rate, it will also change. So unfortunately, there's no well-defined number of segments. And if you compare polystyrene, people measure the, it by different techniques. Some people say 98, some people say 105, and there's not one definite answer. But all people accept it's around 100, plus minus a few degrees. So let's talk about thermodynamics. So thermodynamics for rubber is slightly differs with thermodynamics in the system of the solution, because in that case we only consider the entropy and enthalpy. We consider it to be sort of a semi-closed system, because when you have two beakers, you mix in things, you don't heat it or cool it, or you don't put extra work into that. If everybody learns thermodynamics in your undergraduate class, you could also influence the system by give it work. Work is given by defined by this system of energy. Du can be given by two possible ways you can change it. You can either heat it, or there's inflow of heat or outflow of heat, Q, or you can do different type of work. Work here means we push it. So example would be if you have a gas in a chamber, there is movable piston. If you put the pressure on it, move the piston down. Now the gas is compressed. Your work will be done given by force times distance. Force will be how much force you put on there. The distance will be L. Okay? And this also can be written if you just consider the pressure times volume is the same, because pressure is given by force divided by area, and distance is also related to that. So you can write P times V is related to the force works on the area as well. Okay? So these are similar ways you can write generally how work done into a system can be related to pressure. It's a negative P dV plus force dL. That's the first law of thermodynamics, related to how work can be related to different ways you exert on the system. The second law of thermodynamics is basically relevant to the entropy of states. That will be dq divided by T, or this S dt is what we mostly familiar. That's a unit of energy. So combining them in this equation, we can get the energy of the system is relevant to temperature times S. So temperature and entropy is always related. Pressure times V and F times L. So these are all can contribute to the du. Du means the change of the system's energy. D means delta. That means a small change. And you can see how these are related, all three. And we can link this even to the Gibbs free energy. Gibbs free energy is the same one we talked about in the last lecture. Gibbs free energy, G is related to the H and TS. Here, H is enthalpy. S is again the entropy of the system. And T is the temperature. And if we rearrange a little bit and take a small change in dg, so how this works is if you take a derivative of dg, it will be equals to, if it only have one unit, it will be du. If it's p times v, that means we need to take derivative of p times dv plus v times dp. P times dv plus v times dp. It's just how this works. It's the first derivative of a times b will be equals to a derivative b plus b derivative a. Okay, in this scenario. And you will see in the next slides why we actually want to link the work being done in the system in a second relate to the entropy of the system. Okay, so if we rearrange a little bit, our ultimate goal is to look at how the force is down into the system is related to the entropy and enthalpy of system. So these are the ultimate goal. And the way we go there is using the top equation here. This is what we have seen in the last slides, how delta G is related to system work done in the system, pressure, volume, T is temperature and entropy. If we just do a little bit more arrangement, we can link this delta G, dG, is related to F dL. Okay, so what is the significance of this equation? This gives you understanding how the free energy of the system or Gibbs energy is related to the force down into the system. And at a constant temperature or pressure, your dG is directly related to force and distance. So that means when you pull a rubber band at a given distance, your system's free energy will increase. And this is more or less related to this equation. This means delta dG take a partial derivative at P at constant TL. This is related, plus the second term plus the third term. And most important part is the third term because that's what we wanted. This will be exactly the force related to enthalpy, partial derivative of L, and entropy, partial derivative of L. So there might be quite some equations, but let me explain the physical meaning of this equation. Physical meaning of this equation is, if we know how much enthalpy change per length at a constant pressure or temperature, or entropy change per length at a constant pressure or temperature, we can measure how much force is exerted on the system. And that gets me excited because we can count how much entropy and entropy change when we stretch a rubber, then we can predict how much force we need to stretch on the rubber. Let's take a look at this first. So this would be one of the applications. We can measure at rubber bands when we stretch it. So this will be an example that actually reals data. So this, what I'm tracing, this is F, is basically the stress is being applied to a rubber band. And this is elongation. That means how much we stretch the rubber band. So when you stretch it, you will see more or less it goes like a delta curve, then goes up. It's a little bit S-shaped, but not too predominant, right? So if we separate the entropy and enthalpy term, we can actually do that by looking at the derivative of the measurement at different temperature, the force versus temperature curve. So if we can separate these two, we will see this would be the enthalpy contribution. This would be the entropy contribution. So this curve, if you add this curve, the circle one versus this one, you will get exactly the same. So what this tells you is, at the lower energy state, your entropy has some influence, but you are equally influenced by the enthalpy contribution on the rubber. But at high strain, your magnitude of this curve is much higher than this curve. That means your rubber becomes like entropic spring. So the entropy dominates that your rubber behave like entropy spring. Okay? So let's go back here. And this is very different compared to a metal, for example. So in the metal, so this is an example that you have a crystalline structure of the metal. So the change in the metal comes from the distance change. So this would R0 represents what the distance between each atoms. When you deform, let's say your spring in your car, in your vehicle, there's giant big spring. They're very strong. So when you deform it slightly, what you change is intermolecular or interatom distance, not even molecular in this case. So your atom is being displaced from its lattice. And this displacement has a strong feedback. When I say feedback, because this is a typically plot in terms of energy diagram, in terms of atoms position versus their forces between atoms. You know, atom has very strong interaction. So this R0 would represent bond length. So that's a bond to another bond distance. In this is atomic bond. So when the deformed bond length reaches R0 to R, you can see there's already a strong increase in the force, and this is attractive force because when you get atoms away, they really want to go back where they are before you deform them. Okay, so this explains why atoms deformation is very crucial for the system, for the spring to retract back. And this displacement is usually small. You can't pull two atoms too far away. The crystal will break. So in reality, that represents in the spring, you typically need to coil it up. So when you change the spring, you only apply a little deformation within each cross section. They accumulate over a long distance because you have many coils of spring. So when we heat it, a metal spring, so example would be if we have a metal spring, now I hang 1 kilograms of piece of material below it. So when we change the temperature, when temperature increases, the spring actually will lose ability to hold. The spring gets weaker the higher the temperature it goes. So if let's say this is 100 Kelvin, let's say 500 Kelvin, your spring will relax. This is because it's driven by the entropic. When the entropy increases, your rubber your metal spring, not rubber, just getting weaker and weaker. Okay? So what you're going to learn in a second is if we have a different case, if we have a rubber band, this would be a rubber, and rubber band don't need to be like wavy. We can make just a single strip. Okay, so when we heat up, rubber band has a unique property that it will getting stronger. The rubber band will retract, getting shorter instead of like in this case, it's getting longer. So rubber spring constant drops, but rubber band elastic modulus will increase, make it harder to deform. Okay, these are some of the different. And you will learn the difference because in the metal spring, the force holding it is called entropic in nature. Entropy there means it's just how much force we need to pull to atoms closer or apart. And entropy is just means how much randomness in the system. You will see that for rubber band, that's the case. This will give you another example that for low molecular weight system or for metals, how these would be related. The force will be given by first derivative of system energy, mu, partial derivative r. This will give you what the force will be. Because this is the parabolic shape, we can see that the system's energy will be equals to r minus r0. That will be the equilibrium distance in between atoms. So when you deviate from this r0 distance, or here bond length, your system will raise in the energy. If we take the first law on this particular system, we can get the force will be partial derivative energy to the R. We can get force will be proportional to C times R minus R0. And if you look here carefully, your force is linear proportional to the R. R is deformation. So that means it follows Hooke's spring law. Your spring constant will be just 2C, 2 times C. And the longer the distance, your rubber, no, in this case, the metal gets stronger and stronger. Your force is getting bigger and bigger. Okay? We have talked about this. So in the rubber case, it's different. It's actually entropic driven. The entropy is the main driving force. And if we look at, in this example, this is an example when we have some sort of called thermal inversion behavior. We can see when a stretch rubber band is on the stresses like I show here. When you stretch it a different amount, they would show different behavior. At a very small stretch, it's more or less when you heat at a small window, it's more or less stable or drops. But at higher temperature, your force, your stress increases with within the strain. Okay, at low strain, it's more or less equilibrate or even lose a little bit strain. The lose is because you have an entropic turn still. Entropic turn, if you remember in the last curve, although small but predominant at low strain. A great example would be if this is a 0, that means when you heat a rubber is still going to expand. When rubber expands, it's increase the volume. So if you stretch a rubber at constant, let's say 6%, when you heat it, it will expand. Your force will lose a little bit, but not a lot. Okay, so this will be the stress will be drop a little bit. But if you stretch the rubber 38%, shows down here, when I heat the rubber band up, you can see your contraction force is going up and up. Okay? So this is called thermal inversion. Thermoelastic inversion is only happens in the rubber material. So that means at low strain, your entropic turn dominates and your entropic turn is not coming to play yet. At large strain, your entropy turn dominates and your rubber's entropic turn is not crucial. Okay, so how do we calculate how much entropy we had in a rubber? Amy, you have a question, please.
I have 2 questions. One,
Please.
In the equation for force, you had a term C. What is that?
C is just a generic term when we talk about in the interatomic force constant. That does not apply to our rubber material. I used that as an example to explain the metal material. Okay, so in the case of metal, when you have intermolecular, interatom force constancy, that will impact your force.
Okay, other question. Can you repeat the definition of this? I don't really understand thermoelastic inversion.
Okay, sure. So thermoelastic inversion is basically saying your rubber has 2 components contribute into elastic. There's entropy. Let me write it again. Entropy term, and there's entropy term. Although this term is more or less a constant, it doesn't change with temperature. Entropy term changes with temperature, as a strain. So in this case, when we add low strain, that your entropy term will dominate. So example would be if I pull the rubber just a little bit, Or imagine I didn't pull the rubber, it's just a rubber band sitting there by itself. So when we heat the rubber, there's no change of entropy, right? Because rubber is always a rubber, it doesn't change different state. But what changes to the rubber is it will thermal expand because inter-atom or intermolecular distance will be expand. The thermal expansion will come into play. So that is entropic turn. But entropic turn in this case dominates. But when we start to stretch the rubber more and more, your entropy turn will dominate. Okay? Why? Because entropy goes up with different degree of strain. So this is an example if I show you. If I have a rubber has been pulled at different strain, okay, this is being pulled 3% of original length, this is 6, this is 22, this is 38. So if I pull them at different degree, then I just leave them there. I measure how much stress we have in the system. So that can be done by looking at using a tensiometer, for example. You can do a constant strain, but look at how much stress changes. You heat the system. In a DMA, for example, you can change the temperature from 0 degree to 80. So at the little bit stretch, what we see is your force loaded there, saying there is a slightly drop in force over time, which is unusual because we talked about this happens in metal. When you pull a metal, if you heat up, it will drop because thermal gives the entropic turns, gives the more intermolecular distance freedom to move. So your entropic turn drops. But when we stretch it to 38%, now rubber is stretched, it's unhappy, and entropic force is making it to come back. In this case, when we heat it up, the rubber will getting stronger contraction the higher the temperature is. In this case, we have now an entropy dominated term. Okay? So we're inversion from entropic dominant to entropic dominant. That's what a thermoelastic inversion is. So in one case, it's thermal expansion dominant. In another case, it's thermoelastic dominant.
Okay. I guess my confusion is it seems like there's two terms here. You say like at high strain, entropy takes over.
Right.
But this says it's a stress response with respect to temperature.
No, it's still the strain. Still dominant strain. Strain is one. The response to temperature is just how we measure the experiment. Does it clarify? No?
No.
Let me think about a better way to help you understand this.
Is the numbers on the graph the percent signs? Is that the percent strain?
Yeah, that's a percent strain. So this is a measurement of a sample at 3% strain experience different temperature. Okay, so this is the sample stretched at 13% experience different temperature. So this would be the 38% of strain experience temperature. I mean, basically we see a different slope, right? In the first case, at low strain, we see a negative slope. That means we're dropping in stress with increase of temperature. In this case, we're increasing stress when we increase the temperature. Yeah, Jonathan.
At higher strain, right, it's entropic.
Dominant.
Is that because at higher strain it's kind of stretched out and sort of becomes more linear? And then
Yeah. We haven't get into part. You're totally right. So in that case, you would lose number of configuration in different states.
And that's
So-
why it wants to go up.
Right. So let me try to explain the next few slides. If still not clarified, let me know, Amy. So entropy then in the rubber is directly related to what we talked about in first part of lecture. I hope everybody still remember this part, how chain distribution in a single Gaussian-like coil can depend on how much strain you have. So this is example, probability of distribution of chain end is proportional to, this is normalization factor if we know MB value is, but it will be inverse proportional to R. You can see there negative sign, R square and MB square. So that means the bigger you stretch, there is less distribution in that. And that means you're not in a, your polymer is in adopting a less and less non-ideal configuration when it's elongated or stretched. So in other words, your entropy of the system or number of configurable states drops. So the bigger the pool, the more drop in the delta S. So if we apply this pretty much simple equations, and we could get what in the early days by Walls and Flory and Reiners has described the rubber elasticity theory. They basically said rubber elasticity is related to the loss of configuration states. When you stretch it, your system's entropy drops, so rubber will not be happy or polymer chain will not be happy. It wants to maximize the entropy by restore it back to the original length. And they gave a few assumptions, and the first one is affine deformation. Affine, I kind of give it a blue. Affine is basically says, when I look at my polymer coil, remember there's two scales we are looking at. One is macro scale, basically your rubber band. And there is another scale, which is micro scale, which is if you zoom in, you can see each individual polymer coil, right, between cross-link points. So a affine network basically says, if I pull my rubber band, which is centimeter long, into twice of length, okay, so my nanoscopic structure would also deform by twice. Same. Your constituents copies the macroscopic behavior in that scenario. So that's basically affine. So these are some additional terms. So your segments between the cross links obeys Gaussian statistics, so which is basically what we show. Between cross-link point, because there's tons of cross-link points. If we have something in between, that is, we can show that's a Gaussian behavior. The network is isotropic, and the volume of deformation is constant. And if we all agree those would be reasonable assumptions, we can get S, or entropy of the system, as K ln omega. This is exactly the same what we had described in the last chapter 7. Entropy relationship with number of states, and number of states will be directly proportional to the probability of you can achieve for a polymer chain. Why these can be linked? Because imagine that if you adopt a chain that is less probable, there's not many possible states you can let the chain to configure. So the entropy will be very small because there's only one maybe possible way to arrange for the chain to be fully straight. If you think about the other case, if I'm taking the R, you can have tons of possible ways you can arrange to reach that. That means your entropy is bigger. When P is bigger, your entropy is bigger. So if we apply this simple equation, we can actually relate what the entropy S relate to this particular long equation. I'll explain what each are. So the first part is basically a lowering of this term. This is a constant, so which is given by this part, 2 pi mb squared 3, so which is shown here. And exponent will becomes a constant, right? Then we have minus 3r squared divided by 2mb squared. So the only thing that we need to redefine a little bit is when we deform the rubber, we need to understand what these R0. This will be the Gaussian coil's equilibrium end-to-end distance. This will be equilibrium end-to-end distance. XYZ square will be how much is being deformed in the X direction, Y direction, and Z direction. So if we simplify everything, we will see your entropy of system is related to a constant because R is defined, so this will be a constant. We don't need to worry too much about the first term. Second term is end-to-end distance square and 3k times R. K is a Boltzmann constant. R is basically end-to-end distance vector. This is equilibrate end-to-end distance vector. Okay? So in order to maximize this, R is ideally need to be stay the same. So this will be equals to minus 2/3 of K. If we stretch a lot, R will increase. This will be a very much negative value, right? You will have a drop in entropy in this case. Okay, we're going to cover 2 more slides. Three slides. Let's do 3 more slides. So this is an example that we can calculate in the rubber elasticity theory to look at how much entropy has changed before we stretch it and after we stretch it. So S initial will be representing a coil before we deform it. This will be, think about this will be the 2 cross-link points within a rubber that will adopt this type of shape. And we can assign a coordinate to it. That will be x0, y0, z0. After we stretch the rubber band, we will deform into a new Gaussian Cartesian coordinate will be x, y, z. So how much delta S changed during the stretch is what we are after. So we just need to apply what we learned in the last equation, apply what the final value in delta S minus initial. So in this case, this should be fine NAL, okay? So we apply our final value. This would be our initial value. And constant cancels each other out. So eventually, we only left delta S strain will equal to minus 2mb squared, which replace R0 squared, 3k. And we just need final R squared, which is given by x, y, z squared, because this R squared, this distance will be just exactly as x, y, z squared. Minus, this will be a minus sign here. And initials become positive because there's 2 minus sign. And you can have 3k, 2mb squared. And x, y, 0 means initial deformation. We can further simplify this changes in entropy for a rubber band we stretch after and before by using what we learned from the strain. Strain will be L minus L0 divided by L0. So this will be what we have already defined. Delta L normalized by L0, or draw ratio will be the final divided by initial. So if we apply these steps, we can see the following relationship. So the deformation of the rubber is shown on the left, and what will be after on the right. So we can define the 3 directions in the rubber, the x direction, y direction, and z direction. And we give a subscription of 0, just remind you that's the initial length or thickness, okay? So the rubber band has 3 different directions. Each direction has a given length. After we stretch, this represents the overall length going to be increased. So Lx equals to lambda x times Lx0. So this will be bigger than 1 because we stretched in x direction. Lambda x will be a positive value larger than 1. So you have lambda y and lambda z would be two perpendicular direction. So if we apply this affine network, we can actually use these draw ratio to define what is microscopically. So your change of entropy is given by minus Boltzmann constant, 2/3 mb squared. This will be equilibrium end-to-end distance, and relate to x0 squared, lambda x minus 1, lambda 1 minus 1, lambda z minus 1. And where these come from, so if you look at it carefully, lambda x times x0 will be x1, right? Or just x squared minus x0 squared. The deformation minus what you had before deformation. All right. As I promised you guys, this will be the last slide. It looks like a quite long and lengthy, but don't be scared. Let's talk about what we can learn first. Let's talk about this conceptually. If we sorted out all the words deformation in x, y, z direction, we basically can link the network's entropy is negatively proportional to lambda x, lambda y, lambda z minus 3. And minus 3, this is just initial state. So your entropy of the system is proportional to the strain in x, y, z direction. So if you have large deformation in lambda x, you will have a lot of loss in network's entropy. That's pretty much says the longer you pull, the more you have lost the entropy. But it need to consider lambda y and lambda z, because lambda x is just drawing direction. That's easier to understand. I pull it twice the length, I will have twice the lambda x, right? But how about lambda y and lambda z? They're going to shrink. So these going to come into contribution as well. But how they're going to contribute will be defined in the next slides. So these two are additional terms. And we can link those three together using the constant volume, because lambda x, lambda y, and lambda z are not independent. And lambda x times lambda z times lambda y lambda z will be equals to 1, because you have increasing one direction, the other direction will shrink. And lambda y and lambda z will be equal, because we assume the shrinkage in perpendicular direction will be the same. So you will see this equation, delta s, is basically equals to nk lambda square plus 2 minus lambda plus minus 3. Okay. So this is how this only relate now in one joint direction. Let me rewrite it here. We can start in the next class talk about this. So we basically come into this most important equation of the day is how your strain entropy is related to degree of draw. Joseph?
Is that a plus 3? Why did the sign of the 3 change?
No, didn't, right? Minus 3.
Oh, that's
It should.
minus.
Minus? Okay.
Got it.
Yeah. So if we plot this out, that means the bigger the draw, the bigger the entropy loss. And we had another equation that we can relate. Force is a related partial derivative g with lambda. So in the next class, we will use this equation actually to understand how much force is exerted on the rubber. So that can predict how much stress you could have in the rubber band when you stretch it, depending on the strain. And we will do it this Thursday, okay? So questions, Amy? Any?
No.
Okay. If you have some, let me know. We can continue answer the one you have. But for the inversion part, if you thermal inversion part for the entropic and entropic term, if you have question, let me know. Okay. Otherwise, then let's finish today's class, and then in the next class we will talk a bit more about the theory.